Calculus class, this is lecture 7.1. We are starting our differential equations unit, and we're going to start with slope fields. If you're watching this and you haven't already taken the test for unit 6, please make sure you prioritize that because it's due on 3:30 p.m. on Tuesday. And then if you have already taken it, great, thank you. I hope that you got that submitted on time. And welcome to differential equations. This is our last unit before we start reviewing for the AP Calc test. So, this is going to be a little bit difficult to do without understanding y'all's questions, or I guess not having your questions in real time. So please make sure that you're commenting either on the video or on the Google Classroom form what questions you have so that we can get those answered. Like most of the units that we've done, the conceptual / theoretical part is at the beginning. So 7.1 will definitely be the most difficult. And then after that it gets quite nice actually for differential equations. Please don't panic. A lot of the good things can happen while working from home. For example, Sir Isaac Newton, father of a lot of calculus theory, founded a lot of that theory while he was sent home from Cambridge in his early 20s due to the Black Plague. So, I'm not saying I expect y'all to come back to school with, some new law of optics, but you can dream big, right? We can dream big. This lecture is long because it's worth at least 2 class periods. I'm going to do it all at once. But please know I'm not expecting you to sit here and understand and take in it all at once. So if you watch for the first half and then need to put it away, that's totally fine. But you need to have this whole lecture watched and at least start the 7.1 homework by Friday. So 7.1 is talking about slope fields. Slope fields, they can also be called vector fields or directional fields, are graphical representations of differential equations. What you can think about, right, is when we did our derivatives unit, what we decided a derivative was, and we proved to ourselves, is that it was a rate of change, right? If we took the derivative of something, we were analyzing the rate of change of that function. So if we took the derivative of some f of x and we got f prime of x showed us the rate of change. Now rate of change, when we're dealing with differential equations, we're going to start calling it dy dx. And if you think about dy dx or delta y delta x, hopefully that really closely links in your head to slope, right? Change in y, change in x, or a rise over run is slope. And that's why we call this a slope field. What we're saying is, okay, if we look at a graph, we can analyze what the slope should be, or the rate of change should be at various points along that graph from any sort of parent equation. So these will give us, for the time being, generic solutions, or, when we were integrating in the past, the plus c. Right? So slope fields will show you the plus c version, and then when we have a specific solution, we can graph that as well. So let's start. You'll see there that the first example I gave you was dy dx equals y. So before you panic and don't understand how you see that slope field on y'all's notes, from this, it's okay. All I'm saying is that the change in y over the change of x is equal to whatever the y value is. So, if we set up our graph, which I did there to the right, you don't have to draw this, it's already drawn on your things. But if I'm saying, okay, for all y values of y equals 1, the rate of change is equal to 1. So if you look on your graph and you see y equals 1, that's along this line, right? It doesn't matter what x equals. This isn't dependent on x. It's only dependent on y. Then I have a slope of 1. Let me put this in a different color. a slope of 1. So I'm going to do a tick mark, and in slope fields we do tick marks, like for this exact point, this is about what the slope is. So I'm going to say this is about a slope of 1. And I'll say 1, 1, 1, 1, 1, okay? So this is me showing a tick mark of a slope approximately equal to 1. Please be nice to me as I'm drawing this up on the board and not in my nice notes here. Okay, if we say y is equal to 2, well then we're going to go up to y is equal to 2, and we're going to draw a small line that's about a slope of 2 there. So this is going to be a little bit steeper, right? Right? This is a slope of 1, that's a slope of 2. And then if y equals 3, well, our change in y over our change in x is equal to 3. So that means that this is going to be really steep. It's a slope of 3. Great. Now if we look at a y equals 0, that means that our slope is 0. And if you think about where slope is 0, that is a horizontal line, right? So here, I have horizontal lines because there's no slope there. Then if we have a y equals -1, okay, well then we get, maybe that's a little steep. Do this a little shallower. -1, -1. If y equals -2, it's a little steeper of a negative slope. And then if y equals -3, it's even steeper. So all we're saying is that the change in y over the change in the x, or the slope, for this particular example is equal to y. So whatever the y value is, that's what the rate of change of the slope is at that moment. Man, this is hard without being able to see if you have questions. Okay, so let's go down to the example below and see what we do here. So here it says, example 1, sketch the slope field for dy dx sketch slope field for dy dx is equal to a 3x minus 2. Okay, so if we look at our table, I've already set it up for you, but I say, okay, we have a data table of x, and then dy dx. So what you're going to do, you can see I already have a graph there to the right for you, and it goes from -2 to a +2. Okay, so let's do -2, -1, 0, 1, and 2 for this slope field. So if I plug in a -2 for my x, I should be able to figure out what the slope is at that x value. So if I plug in a -2, I get 3 times -2 minus 2. That is equal to -6 minus 2, -8. So it's a very steep slope. If I plug in a -1, 3 times -1 minus 2, I get a -5. If I plug in 0, 3 times 0 minus 2, I get -2. If I plug in a 1, I get a +1. And if I plug in a 2, I get a +5. So in this first example, all of the slope was dependent on what the y value was, right? Which makes shows you that as you change in x, all the slopes along that same y are the same, right? All of these were a slope of -3 because the x didn't do anything to our slope, only y does. This will be the opposite, where y doesn't do anything. So we're gonna see the same slopes going up and down. So for all of x equals -2, we have a really steep slope of -8. This is gonna look like a vertical line, but please be aware that it's not. There we go, that's my slope of -8. At -1, I have a slope of -5, so again, it's really steep, but less steep than this. At 0, I have a slope of -2. At 1, I have a slope of +1, so I can flip this way. And at 2, I have a slope of +5. So there is my slope field. So when I ask you to sketch a slope field, what you should do is realize that what I'm asking is for small dashes at certain points of x and y that represent what the slope is at that point. So if it's a really steep negative slope, do your best to show me that. And then make sure that you're aware of, positive and negative, so on and so forth. This is a slope field here. Now should I tell you? Should I ruin the surprise? Yeah, let's do it. So why does this matter, I guess? Let me show you. If we take this equation and we get all the terms with respect to x on one side and all the terms with respect to y on the other side, what we need to do for this one is say, okay, let's multiply each side by dx, right? Because then this dx cancels out. And we're left with dy equals dx, or sorry, dy equals 3x minus 2 times dx, right? That's just me multiplying dx on both sides. Now, if I integrate both sides, I have the integral, both sides. The integral of nothing dy is just a y plus, we'll say c1, because it's some constant, but I don't know what the constant is. And on the right, I have this integral, so that is equal to a 3 over 2x squared minus 2x plus some c2 constant, right? Because we have no bounds of integration on either of these. So if I solve for y, I would subtract a c1 from both sides. And I get that y is equal to a 3/2 x squared minus 2x and then plus some c3 constant. A constant that we don't know minus a constant that we don't know just becomes another constant that we don't know, so you can just keep changing the notation on the c. So now if you look at this, we have essentially an equation that is clearly a quadratic. Now if you look at the slope field and you decided to try to draw a curve, that matches this slope, you have to follow the slopes. Let's just pick a random point. I'll start here. I'm going to go along this slope curve, and then I have to somehow come up because now it's down to this slope curve, and then this slope curve. This is what type of graph? Hopefully, you're noticing that we've created a parabola. What does this tell you that our graph should be? A parabola. Now it's saying plus C3 because this graph actually shows us I mean, if you did the graph of everything, it would show you an unlimited amount of solutions, but this is showing us like 5 different solutions, right? If we decided to shift this C, your graph would shift, right? It might be it's now this solution. You're following your slope curves and you're coming up like this, right? So this is another parabola, but if your constant is different, what your parabola does is also different. It's kind of neat. So this is what a slope field is. It's saying, okay, given some equation, we can figure out the rate of change, and then if you integrate, that gives you then what your original function would be. This is a generic solution with C3. But then if I asked you, okay, what's the rate of change of this, what you would have done was taken a derivative. You would have gone backwards, right? And you would have ended up with this. And you'd say, oh, the slope here is this, and the slope here is this, and now the slope's changing, so on and so forth. So that's what slope fields are. Conceptually. So those were 2 pretty easy ones because we had one slope field that only relied on y and one slope field that only relied on x, but as you can imagine, that's certainly not always the case. Actually, it's almost never the case. Usually it's going to depend on both x and y. So let's go on to example number 2 here. For example number 2, I say to sketch the slope field and then use integration to solve for the general solution, which is what we had just done over here, for this differential equation. 2x minus y dy dx equals 0. Now usually it's easier for me to figure out the slope fields if I solve for dy dx. So I'm going to say, okay, 2x is equal to a y dy dx. Whoa. There we go. Just added that term to this side. And now if I divide by y, I'll solve for dy dx. So dy dx is equal to a 2x over y. Now here's the complicated part of this one that the other graphs didn't really show you. Okay, if I ask you to only go from -2 to +2 in x, that's one thing. But now for every one value of x, let's say -2, we have 5 values of y, right? 1, 2, 3, 4, 5, because I'm also asking you to go from -2 to +2 in y. So if you look at the table that I gave you in your notes, there is not enough slots in that box to figure out the slope at every single one of the x and y points. You can do that on scratch paper if you want. I'll be doing all the points, so maybe if you want to just pick a couple from each one, or maybe once I go through one whole thing and you understand how to do it, you're fine. But if you want extra room, maybe go to the left of it and draw another box, and then you extend your box down as much as possible because we'll have several points here. Okay, so if I have x, y, and then what I'm looking for, which is dx dy. Let's go ahead and start with x being -2, and I'm going to do all my y values for that. So if x is -2, I'm going to have a y of -2, a y of -1, a y of 0, y of 1, y of 2. Okay, so what I'm looking for are essentially these slope points right here, if that makes sense. Okay, so looking at this equation right here, if I plug in a -2 for x, I get -4 over -2, so -4 over -2, that is equal to a +2. Okay, If I get a -4 and now over -1, I get a +4. If I have a -4 over 0. Interesting. 4 divided by 0 does not exist. If I do a -2 as x, I get a -4 over 1, that's a -4. And then if I do a -4 over 2, that's a +2. Okay, so now at each of these coordinates, right, each of these is just a coordinate, I'm going to draw this slope. Let's really quickly think about a does not exist slope though, because how am I going to draw that? What this is saying is that for my rise of -4, I run nowhere. I run 0. So that means that I am rising and falling. In this case, I'm falling a -4, but I haven't moved. So let me try to show you with my body what that is. If I was falling a -1 and going left a -1, I would start here. I would fall 1, and I would go over 1. So I have a slope. Now, if I have a fall of -4 and a run of 0, all I do is go like this, right? So, hopefully, man, this is hard. Hopefully what that shows you is that if you have a slope that doesn't exist, what that means is that you have a vertical line, right? Because you have all rise, but you have no run. So this is a vertical line. Okay, so let's go. -2 down to -2, and I have a +2 slope. So I'm going to do that. -2, -1, I have a +4 slope. So this. At -2, 0, I have a vertical line. At -2, +1, I have a -4 slope. And then at -2, +2, I have a -2 slope. Okay, not bad. Let's go ahead and do values for my -1s. So now I'm just going to do all my x equals -1s and fill in all my y's there. So if x equals -1, my top, for this situation, my top will always be a -2. So -2 over -2 is equal to a +1. -2 over -1 is equal to a +2. -2 over 0, this is another does not exist. A -2 over a 1 is equal to a -2, and a -2 over a 2 is equal to a -1. So now I have these 5 slopes for these 5 points, and I can go over and graph those. So if I have x is -1, y is -2, I have a +1 slope. If I have x is 1, and I have positive, and I have a +2 slope. I have a straight up and down line, again at 0. Then I have a -2 slope here. And then I have a -1 slope here. Okay. Yay! Let's do my x equals 0. These ones will be easy. I'm not even going to fill in the table for these. Maybe let's fill in 1 so that you know. But if all my x's are 0s, then I get 0 divided by everything. So let's just do the -2 point. 0 divided by anything is equal to 0. So now this is saying that I don't rise at all, but I'm running forever, which does sound a lot like my life. Just kidding. But this essentially means, right, the opposite. Instead of a vertical line, this is a horizontal line, right? So I'm going to go to x equals 0, and I I know this looks like it's just following the hash marks, that's not on purpose. These are all zeros. Yay! This technically at 0, 0 has both a horizontal and a vertical asymptote, right? So this can't cross or even touch at that point in any direction. Okay, let's do our positive x points. If we're doing our positive x points, let's do 1. Okay, if we plug in 1 for the top, we'll get a 2 every time on the top, and so this is a 2 over negative 2, that's negative 1. 2 over negative 1, that's negative 2. 2 over 0 is again, does not exist. 2 over 1 is a positive 2, and a 2 over 2 is a positive 1. I'm going to go ahead and do my 2 points. Okay, if I plug in 2 for x, I'm going to get a 4 over a negative 2, that's negative 2. 4 over negative 1 is negative 4. 4 over 0 does not exist. 4 over 1 is a positive 4, and 4 over 2 is a positive 2. So I'm going to finish up my slope field here. 1, negative 2, I get a negative 1 slope. Then I have a negative 2 slope. Then I have a does not exist straight up and down. And then I have a positive 2 slope and a positive 1 slope. Okay? And then going down to my 2 points, 2, negative 2, I have a negative 2 slope. I have a really steep negative 4 slope. Then I have a does not exist. And then I have a really positive 4 slope, and then a pretty positive 2 slope. So there is my slope field for this one. Now the next thing it asks us to do is to use integration to actually solve for this, right? So if I'm integrating, I need all my y terms on one side and all my x terms on one side. So if I take this equation, I have a 2x on this side, but the dx is on this side, so I need to bring it over. I'll multiply both sides by dx. So I get 2x dx is equal to y dy. Welcome to differential equations. All it is integrating both sides. Pretending it's just like any other mathematical operation. Integral of 2x is x squared plus c1. A million bajillions of points taken off if you forget your constants throughout those problems. This is equal to a 1/2 y squared plus c2. Now, let's solve for y. So I'm going to subtract c2 from both sides. I get x squared, c1 is an unknown, c2 is an unknown, so I'm just going to have some new unknown, doesn't matter what it is. I'm sorry, it very much does matter, but we can't, you don't have to put c1 minus c2 in parentheses, just say that it's c3. Is equal to a 1/2 y squared. So I'm going to multiply both sides by 2. So I get 2x squared, and then 2 times c3 is again just some other constant, so I'll just bump it up to a c4 at this point, is equal to y squared. And then I will take the square root of both sides to get y on its own. So I get plus or minus the square root of a 2x squared plus c4 is equal to y. See if that makes any sense. If you look at your graph, y is a plus or minus, so it does go plus or minus. We're seeing slopes on plus or minus side. And then if you were to pick a point and follow the slope field, Man, this is really hard without a nice graph. These are all very steep and becoming shallower. So if I tried to start at 0, 0, technically you'd start right after it and you would get going steep, and then here it's starting to slim down. And then if we were to keep going, this one is hard for me for some reason to draw in this slope field, probably because I don't have enough points. So maybe we'll just leave it alone until we get a larger graph. Okay, we're done with that example. Let's move on to a new example. Example 3. Consider the following equation. dy dx equals a negative x over y. Compute dy dx at each set of points and then answer the following question. So, if I have x, y, then I want you to compute dy dx, and I want 1, 1, negative 1, 1, negative 1, negative 1, and 1, negative 1. What you'll notice, right, is that this is first quadrant, second quadrant, third quadrant, and fourth quadrant on our graph. So if we plug in 1 for both x and y here, we end up with a negative 1. Here, we'd end up with a positive 1. Here, we end up with a negative 1. And here, we end up with a positive 1. Simply plugging these points up in there. So, if we look at this, we can see that dx, dy is positive in quadrants 2 and 4, but negative in quadrants 1 and 3. Now, I ask you to do this again before a new set of points. This is a little bit lower on your paper, but I'm just going to extend it out. 1, 0, 2, 0, negative 1, 0, negative 2, 0. Now, we've already done this analysis, but just to drive the point home, no matter what I plug in for x, it's always going to be over y, which means that all these values do not exist because that would be dividing by 0, which means here that we have a undefined slope y at y equals 0. These are vertical lines. When you compute something and you end up with dne for the rate of change of the slope, that means it's a vertical line. Conversely, if we were to calculate going down even below, oh, I also ask you, what happens if the slope is 0? Right, so if we, for some reason, we're doing x equals 0, that would be horizontal lines. So if you get does not exist, it's a vertical line. If you end up with the value 0 for your slope, that doesn't mean it doesn't exist, it just means that your slope is 0. Okay, for the next ones, I ask you to do 1, 1, 2, 2, negative 1, negative 1, And lastly, negative 2 comma negative 2. So this is when x and y are the same, right? So if I plug in x and y both as 1, I get negative 1. Both as 2, I get negative 1. Both as negative 1s, I get negative 1. And both as negative 2s, I get negative 2s. So for all of these, if you're looking at those, what equation would express dy dx equals negative 1? Where it's where x is equal to y, right? X is equal to y in each of these cases, and I got negative 1 in each of these cases. If I wanted to figure out in what case could I get positive 1s, I would have to switch one of the x or y values to be negative. So if it says, how could you get dy dx to equal a positive 1? Well, you just need to have either a negative x comma y or a positive x comma negative y. Right, if you do negatives in just one value, like here in quadrant 4 or here in quadrant 2, you see we got positive 1 slopes here. Okay, now let's work a little bit with the slope field for this. Whoa. Okay, part D, use the grid at right to sketch the slope fields for the values that you calculated in A, B, and C. So you have the data tables in A, B, and C, I just erased them, but let's go ahead and sketch that. Okay, I'm going to start up at part A. So for the point 1 comma 1, I get a slope of negative 1. For the point negative 1 comma 1, I get a slope of positive 1. For negative 1, I get a slope of negative 1. And for positive 1, negative 1, I get a slope of positive 1. Okay. At any point where x equals 0, I have where y is equal to 0, I have a straight up and down line, so that's kind of already done on my graph by the hash marks. You can leave yours as the hash marks if you want to, or draw it for this. And then everywhere where I have the x equals 0, it's a horizontal slope. So the tick marks, again, already fill out those points for me. So let's now do, I see I have a 1, 2, comma 2, and that slope is negative 1. I have a negative 2, comma negative 2. Okay, I don't really have that many points. Maybe let's do a few more points in the data table. So if you have, dy, if you have x, y, and then dy, dx. Let's do a couple points on negative 2 and a couple points on positive 2. So let's do negative 2, positive 1, negative 2, positive 2, and negative 2, negative 1. And then if we do a couple positive points here, let's do positive 2, positive 1, positive 2, negative 1, positive 2, negative 2. So I'm just filling in this graph a little more. So if my equation is dy dx equals a negative x over y, so I get a negative negative 2, so that's a positive 2 over 1, that's equal to 2. We have a positive 2 over 2, that's equal to 1. If we have a negative, that's a positive 2 over a negative 1, so that's negative 2. Negative 2 over 1, that's also a negative 2. Negative 2 over negative 1, that's a positive 2. And a negative 2 over negative 2, that's a positive 1. So now I'm gonna just graph a couple more slopes here. So at x equals -2, 1, I have a +2 slope. -2, 2, I have a +1 slope. -2, -1, I have a -2 slope. At +2, +1, I have a -2 slope. +2, -1, I have a +2 slope. And at +2, -2, I have a +1 slope. So now this is starting to look a little bit more filled in. If y'all want to fill in more to see the fuller picture, but if we do now, draw the particular solution that passes through the point 0, 2. So if I find that point, that's 0, 2, right here, you try your best, and this is kind of hard, but to follow the slope lines. That doesn't necessarily mean this will connect to each one below, but it does mean the slopes at that point are the same. So the slope right here is flat horizontal, and then it starts to turn, and then it turns again, flat horizontal again, and then it's following these ones. Nice. Not perfect because I'm not on a graphing paper, but this would be a particular solution for 0, 2. If I wanted to do a particular solution for 0, 1, I would start here and I'd do the same thing. I would come across and try to follow the slope lines and what they're telling me to do across like this. So if you notice, what this is not a great picture of, but it's supposed to look pretty similar to a circle. Let's prove it by figuring out the equation, right? So if we have dy dx equals a -x over y. Well, in order to solve for this, I have to get all the y terms on one side and all the x terms on the other side. So I'll multiply both sides by y, and I get y dy dx equals -x. Then multiply both sides by dx, so I get y dy equals -x dx. Now I'm allowed to integrate. So I get 1/2 y squared plus c1 is equal to a -1/2 x squared plus c2. Awesome. Because I know that this is a circle, I'm going to start solving this not for y, but for the equation of a circle. If you didn't know that, I probably would have started solving it for y and then realized. So I'm going to subtract c1 from both sides. And I'm going to add a 1/2 x squared to both sides. So I get 1/2 x squared plus 1/2 y squared equals some unknown constant c3. Can go ahead and multiply the whole thing by 2. So I get x squared plus y squared equals 2 times c3, which is an unknown, so I'll just say c4. And I'll be darned, that is an equation for a circle. If you wanted to find out the particular solution, like part D asks us for the particular solution through point 02, well then let's just plug in points for that. Particular solution is 02, so we get 0 squared plus 2 squared is 4. So then we would say, okay, x squared plus y squared equals 4 for our particular solution. So this is general, and this is particular. Now let's double check. This says, okay, I should have a circle with a radius 2. This could be better, but it is a circle with a radius 2. It's just not drawn very well. Great. Okay, let's finish up this example, and maybe that's a good stopping point for the day, unless you're excited and want to keep going. Okay, so G says, explain what happens to the slope values as you move from left to right with a fixed y value. Okay, so if you look at equation or example, not even an example, the very first paragraph of your notes, right? Everyone flip back there. And you see the slope field that I put there on your paper, and it says dy dx equals y, right? So this is an equation where the y value is fixed. So as x increases, so you're looking from left to right across your graph, what is happening to y? Uh-oh. Okay, sorry about that. If you're looking, was this what I want? Oh, with a fixed y value. Yeah, so if I'm looking across from left to right, so as x increases, the slope, or dy dx, does what? I'm letting you hopefully think about this. Oh, we shouldn't do that. We should do, oh, for this specific example. I'm so sorry. So instead of looking at the very beginning of your notes, let's actually look at the example that we're doing, because that one doesn't change if it's a fixed y value. So instead, if you look at your slope field for your circle that you've drawn, let's pretend that we have a fixed y value. So let's say that y equals 1 for this example. If we have y equals 1, what happens to the slope as we go from here to here? Well, here, it's steep. It's getting shallower and shallower as x is increasing, hit 0, and then it starts to get steeper and steeper, but in the negative. So what that says to me, this is part G, is as x increases, dy dx is decreasing, right? So we started here, and our slope goes for a fixed y point. So I'm looking only at y equals 1, for example. We're fixing it. It starts here, and it's going to get shallower and shallower, and then it's going to get more and more negative. So it is decreasing. Let's look at it the other way. As if you fix a value of x, so let's look maybe here at x equals 2. As we go from the x-axis, so it's asking us to look from here, and then as y increasing, what happens? Well, here, it's straight up and down, and as you go up, it's starting to flatten out, right? So as y increases, looks like dy dx flattens out, which is approaching, a horizontal line there, right? And if you go up, up, up on here, it's approaching a horizontal line, which makes sense because you're supposed to be making that turn for a circle. So eventually, you have to hit a horizontal line, otherwise you won't create a circle. Okay, good job. The only other things that we're going to do are a matching, which does take a little bit of finesse, I would say. And then we'll do one full example of a differential equation and then wrap things up. So this is the second half of this lecture. Slope fields. This matching one is going to be extremely difficult for me to draw up on the board all the slope fields. I don't think that I'm going to be able to do it. But I'll give you some tactics. So if y'all are looking at your papers and you see graphs A through H, I'm going to tell you my tactic for how I would match these. First thing I would do is look through the graphs and see if there's any off the bat that I'm like, oh, I know what the graph of that is. Really good indicators are when something can't exist. So for example, D and E have clear sections where a slope field doesn't exist. And when I say doesn't exist, I'm not meaning a vertical line. I'm meaning like it can't be graphed. What that means is that your original function must have a limit where values can't exist. So if you look at your equations there, 1 through 8, you have a square root, you have an exponential, a sine, a cosine, a natural log, a y squared, an xy, and a cosine of x plus y. There are 2 equations in there that have limitations on values that can exist. Let me think really quickly. Look through those. The most obvious one that jumps off the bat to me is number 1. Right? Number 1 is a square root function, which means that if you have a negative underneath that square root, you have an imaginary number. So that to me means that 1 must be either D or E for my graphs. Number 5 is the other one, right? We can't have natural log of a negative number. So we need to have, if we look at, so I guess the first tactic I would use, maybe write this in the space underneath. Tactic 1, look at graphs and equations to see if there are limits of x and y values. Right? So this is the first thing. So for example, number 1 is dy dx equals the square root of x plus 2. Well, I can't have a negative square root, so off the bat I know that this has to only have a slope field for all values where x has to be greater than a negative 2. Right? Because if it's negative 2 or less, this will be a negative square root and that can't exist. So for me, that looks like D. And then if you look at number 5, you have dy dx equals natural log of y over y. Okay? Well, for natural log of y over y, 1, it can't equal 0 because you can't divide by 0. And then you can't have any negative natural logs. So this one looks like we need to have y that are greater than 0. And that is graph E. Okay. That's step 1. So you can go ahead and cross off E and D. The next thing I typically do is I just look really quick at the graph of the slope fields and I just see, is there any in there that immediately jump off to me as a parent function that I would know? So like for our last example, if I notice that it's a circle, could I go over and look at the equations and see that if I integrated it, does it become a circle? A, no idea. B, no idea. C, to me looks like a cubic, right? So let's do that. Look at graphs and equations to see if any recognizable Okay, so for me, if I look at C, that to me looks like a cubic. Now if I look at my equations on the right hand side, just looking at those, is there any of those that jump out to you, like if I integrate this, it will give me a cubic function? The answer should be number 6, right? If you look at number 6, that says that dy dx is equal to y squared plus 1. Well, if you integrate a y squared, you're going to get a y cubed. So, and then C looks like a cubic function. So I would say that that is pretty safely C. Okay, we've already done D and E. If I look at F, not sure about F. If I look at G, I'm completely flummoxed. If I look at H, I'm pretty happy. H to me looks like a sine function. So I need to go to my list and see, is there anything up there that if I integrate it would give me sine? Number 4. That one says dy dx is equal to a cosine of x. If you integrate cosine of x, you end up with sine of x. So that is graph H. Woo! Okay, just like that, by visually inspecting, we were able to pick out 4 out of 8. That's a 50%. Could be worse. The unfortunate next step for graphing, or for matching, is needing to integrate the other ones that are left and then graphing them yourselves. So, yuck. Integrate remaining equations and graph a solution. Fun. Okay, so let's start off with, what did we do? We already have number 1, so let's start off with number 2. Number 2 says that dy dx is equal to xe to the negative 0.2 x squared. Yeah. Okay, so I need to get dx to this side, so that becomes dy is equal to xe to the negative 0.2 x squared dx. Now I can integrate both sides. I don't know how to integrate this, so I need to set up a u. If I say that u is equal to a negative 0.2 x squared, then I get du is equal to a negative 0.4 x dx. If I solve for dx, I get dx is equal to du over a negative 0.4 x. Integrating y, integrating 1 dy, I get y plus c1. So that side's easy. On this side, I'm going to plug this all in really quick and see what it turns into. So I end up with x e to the u, and then dx is equal to du over a negative 0.4 x. So my x's cancel out, which is what I needed them to do. And I end up with a 1 over negative 0.4 integral of e to the u du. If I integrate this, I end up with y plus c1 is equal to a negative 1 over 0.4 e to the u, which is negative 0.2 x squared, plus c2. So I end up with y is equal to a negative 1 over 0.4 e to the negative 0.2 x squared plus c3, some unknown. That's my equation. Who knows what the graph of that looks like off the top of your heads? I do not. So I'm gonna bust out my handy dandy calculator. And I'm going to graph it. Y equals. Shouldn't put things in your mouth with coronavirus, so I'm not going to do that. Okay, -1 over 0.4, and then times, be very liberal with your parentheses, please. Okay, graph it. I put in nothing for C3, so I did a particular solution where C3 was equal to 0. Please do that as well. All you want is to see one solution and see if you can match it to the slopes. So when I look at my calculator, and I hope y'all are actually looking at it on your calculator, what this looks like for me is this. If you're not seeing all of it, please press trace on your calculator and scroll over till it will zoom out for you. But I'm looking at this on my calculator, and that to me looks like A. Woo! Okay, so now we have 1 done, 2 done, 3 not done. We're gonna have to skip 3, that's the last tactic. 4 done, 5 done, 6 done, 7 not done. Let's do 7. What you got for me, number 7? Number 7 says dy dx is equal to -xy. So I'm going to have to divide both sides by y, so I get 1 over y dy, multiply both sides by dx is equal to -x dx. Now that I've separated my variables, I can go ahead and integrate both sides. The integral of 1 over y is natural log of y, right? Plus c1 is equal to a -1/2 x squared plus c2. If I subtract c1 from both sides, I get the natural log of y is equal to -1/2 x squared plus c3. I have to take e to both sides. Woo, okay, I get y is equal to e to the -1/2 x squared plus c3. Going back to the handy dandy calculator here. Y equals e to the -0.5 alpha x squared. Again, I'm gonna not put anything for C3 because I just want one generic solution. So I'm going to go ahead and graph that. Okay, I got this type of graph. So if I look at my graphs available, that looks most like B. If you want to change the value of C3 to something crazy to see if you can get another solution but in a different portion of the graph in your window screen, please feel free to do that. Okay, so now the unfortunate thing is that we are left with 3 and 8. And those options look like they could either be F or G. Now watch if I try to do 4, or sorry, 3, option 3 for these. All right, if I have dy dx is equal to sine of y plus x. This is, what is this, number 3. You could try this, but what I hope you would notice is that there's no way for me to separate these variables. Right? If I multiply this by dx, I have to multiply this quantity by dx. And then there's no way for me to pull then out sine of y. So if you cannot separate variables, which you can't for 3 and you can't for 8, then you go to my last tactic, which is pick an easy slope from the slope field and plug in points. Okay, so we're left with 3 and 8, where they are dy dx is equal to cosine of x plus y. And I'm looking at the only graphs available to me are what's not canceled out, G and F. So I'm going to go ahead and look at the slope or the slope field for F. Now, if I look at the slope field for F, if you look at point 0, 0, everyone looking at the origin on that slope field, it looks to me that at 0, 0, I have a slope of about 1. So on graph F, at point 0, 0, dy dx is equal to about 1. Now what I'm going to do is say, okay, if I plug in 0 for y, right, 0 for y, I get sine of 0. Sine of 0 is not 0, or sorry, not 1. It is 0, the exact opposite. So I essentially get a 0 plus 0, so dy dx would equal 0. Does dy dx equal 0 on that slope field? No, it doesn't, which means, let's plug it into here. If we get cosine of 0 plus 0, we get cosine of 0. Cosine of 0 is equal to 1, which means that I think that graph F goes with number 8. If we look at our last graph, which is graph G, let's pull out an easy point from graph G. So to me, it looks like at 0, 0 for G, I have a horizontal line. Dy dx equals 0. Perfect. If you plug in 0, 0 for x and y here, you get sine of 0, which is 0, plus 0, which is 0, so you get 0. So I think that this has to be G. So matching problems, maybe up until this point, have been fun. I'm not saying this isn't fun, but they can sometimes be a little bit of work, right? That took us a significant amount of time because there's a bunch of different tactics. Tactics 1 and 2 are really easy and quick and should hopefully get you at least halfway there. Tactics 3 and 4 are a little bit more time intensive. Okay, last thing, y'all. Okay, example 5. A differential equation, a point, and a slope field are given. Use the slope field to sketch a particular solution through the point. Then use integration to find the particular solution of that differential equation point. Okay, so use the slope field to sketch a particular solution through the point. So the point, oh man, I don't have my graph. Okay, I don't have my graph, y'all do have your graphs. But the point it wants us to go through is point 0, 1. So please go up to 0, 1 and try your best to give an equation or draw the line based on the slope field there. Please be very careful with what is happening at x equals -2. Right? To me, it looks like we have a undefined slope there, which would be an asymptote. So if I'm then looking, I see that I have very shallow slopes here, and they're getting steeper and steeper, and then I can't cross my vertical slope line there. So this is my best guess for what this graph looks like. Okay, so use the slope field to sketch a particular solution. Done. Then use integration to find the particular solution. Okay, so we have dy dx equals a 1 over x plus 2. Great. I need to just multiply both sides by dx to get all my x terms on this side. So I have dy equals a 1 over x plus 2 dx. Let's go ahead and integrate both sides. The integral of 1 dy is just y plus c1 is equal to a 1 over x plus 2. Let's go ahead and say u is equal to x plus 2, du is equal then to just 1 dx. So I get the integral of 1 over u du. Now I can integrate that, so I have y plus c1 is equal to the natural log of u, which is x plus 2, and then plus a c2. I'll go ahead and bring this c1 over, and I get that y is equal to natural log of x plus 2 plus a c3. Now, we are asked to find a particular solution. C3 is a generic solution. So what we need to do is use our point that we're given, right? This is 0.10, to figure out what C3 is. So if we plug in 1 and 0 here, we get that 1 is equal to the natural log of 2 plus C3, or that C3 is essentially 1 minus the natural log of 2, which is just some number. I don't expect you to plug that in your calculator. We can just now plug that in for this. So we get that y is equal to the natural log of x plus 2 plus 1 minus the natural log of 2. And that is our particular solution. Let's go ahead and double check that what we graphed on our slope field actually looks like that. So we're going to bust out your calculators again, go to y equals, and let's plug in our new function. Y equals the natural log of alpha x plus 2 parentheses plus 1 minus natural log of 2. Graph. Can you guys see this? That is, look at this. Look at those. Those are about the same. Yeah. Woo! We are geniuses. Boom. Okay. How to distinguish between slope fields. This is just a quick summary. One thing that you should always note is if dy dx has only x, so if you say dy dx equals and there's only x, this is like example 1 in our notes, then the slope changes left from left to right only. Let's go ahead and look really quickly at our notes, example number 1. if you go in your notes, example number 1, dy dx equals 3x minus 2. That is only dependent on x, and you'll see that as you go up and down, the slope is the exact same. It's only as you go from left to right where that's different. Conversely, if dy dx has only y, the slope changes from up to down only. And that's like that very first paragraph of this section before we even started taking notes. If you look from left to right, the slopes are the same, but as you go up and down, the slopes change. Obviously, if dx and dy has x and y, everything should be changing at all times because it's got a relationship to x and y. So some things that will make your life easier is find what conditions for x and y, like what x and y points. What conditions will make. And there's a couple of things that you can like try to force x and y to become so that you get, is there certain x's and y's that will make dy dx equal 0? So you can look for, your horizontal dash marks. Are there certain x's and y's that will make dy dx undefined? So you know that you'll have vertical tick marks there. And then you can always look for positive and negatives, right? Are there certain values for x and y where you will always be, positive slopes? And are there certain values for dx and dy where you will always have negative slopes? Okay, y'all, that is it. It's all you need theoretically for homework 7.1. So please go ahead and get started. Please comment with questions so that we can all help each other out. I'll make this, I guess it depends. This is spring break now. Oof. Okay, this is spring break. So if we come back to school after spring break, it will be due the Wednesday that we are back from spring break. So we'll have Monday and Tuesday in person, but please try your hardest. And we'll just hope for that. We hope we come back after spring break. Bye, y'all.